Alaikum wa rahmatullahi wa barakatuh. Good morning, class. Welcome to the secondary school platform once again. We are continuing with our study of current electricity. Mr. Chitani Rashid, as usual, is your presenter. I'm happy to relate to Mr. Sisechid Mustafa here for technical assistance. Good morning once again. We left two activities in the previous lesson. The first activity was connected with power and energy. Then the second activity was to do with electrical costs. Today we'll be handling mainly application of electrical heating and domestic wiring. Before we go to that detail, let's handle activity 1. In our activity 1, we had number 1, the circuit in figure 1 below shows resistors connected across a cell of EMF 5 volts and negligible internal resistance. The current in the circuit is 0.2 amperes. Find the value of R and hence the power dissipated in R. The notes are attached, are uploaded, and they are we have started on slide 62 for the activity that you had previously. So the circuit was like this: 5 volts. Now the parallel setting here of unknown resistance R and another known resistance which was 20 ohms. Current through 0.2 amperes. Then we had another resistor here of 15 ohms. So the first part of the question was saying, find the value of R and hence the power dissipated in R. Now, to find the value of R, there are two approaches. One is the first approach is to know that if you have the EMF of 5 volts, there is the EMF, there is PD used here and the PD used here. So the sum of the PD across the parallel circuit plus the sum of the PD across the 15 ohm will give us the total PD of 5 volts. So let's get the PD across the 15 volts. PD across the 15 ohm, which we call V2, is equal to I R2. The current I is 0.2 and the resistance is 15. You won't help me with the calculator if you have. So 0.2 times 15 gives what value? 0.3? 3 volts. So if there are 3 volts here, it implies that PD across the parallel is going to be 5 minus 3. Therefore, PD across the parallel setting is going to be equal to the supply of 5 minus the one that has been consumed here, which is 3. So we get a total, a PD of 2 volts. This is now the PD across the parallel setting. So now we can now come here and then say that current through the 20. Therefore, current through 20 ohm is going to be equal to V, I call it V1 over R. The R, it's R20. So that is going to be equal to 2 divided by 20. You get the answer to be 0.1 ampere. So if you have now got the current across the 20, you remember this current here was coming like this. It's subdivided into 0.1 now. Are you getting that? So what do you think is the one going through R? 0.1. Therefore, current through R is 0.2 minus 0.1, which gives 0.1 ampere. So therefore, value of R is equal to V over I. If the V is now 2 and the I is 0.1, this gives 20 ohms. You see that? So that is one approach. We can try out. Are we convinced with the first approach? Are we convinced with the first approach? Someone is saying the approach is complicated. We are repeating. We are saying the total EMF is 5 volts. Are you getting it? And the current, total current supplied is 0.2 amperes. So EMF is the sum of the individual PDs, the PD across the parallel setting and the PD across the 5. Are you getting it? So when you add V1 plus V2, you get 5. But the fact that we know current and the resistance, we can find the PD across this one, which we did and found it to be 3. So that means the PD for this one is going to be the total minus the PD here, and remain what? 2. That means the voltage, 2 volts, is the PD across the parallel. Are you getting it? So therefore, current through the 20, which is in parallel, is going to be equal to V over R, meaning that the V 2 over the R20, which is already here. So that we can get the current through the known resistor 20. If we can now get the current through the known, we get this one, subtract off, because this current here subdivided into 2. The one here and the one down. Of the 0.2, the 20 consumed 0.1. The remainder passed through R. In fact, at that point, only knowing that this is 0.1 and 20, automatically when you say now this is also 0.1, automatically tell you that the other one is also 20. Negative. But not taking things for granted, that's why we are saying current through R, which is unknown, is going to be 0.2, subtract off the one that has been consumed by 20, the remainder will be for R. Then, value of R is V over I. The V we are talking about is the V across the parallel. This one, actually we had called it V1 over I. You can call it anything, but the I is 0.1. and we get the answer to be 20. Are we now okay? That is one approach. I don't know whether that one will be the one familiar to you. The second approach. Second approach is a bit mathematical. Now we said for two resistors in parallel, the resultant resistance is product over sum. Isn't it? The resultant resistance is what? Product over sum. So you can now get total resistance in the circuit. Total resistance is going to be product over sum 20 R over 20 plus R plus 15. You get that one? Now, like I said, it's more mathematical. If you are not mathematical friendly, I'll give you some hard time. Okay, I've got the LCM to be 20 plus R. Okay? So this 20 divided by that one will make 20 plus 20 R. And then that one is going to be having 15 into 20 plus R. Yeah, mathematical. Don't accept to please me. Because when you praise me, I don't benefit. But if you are contented with what I'm talking about, then you can continue. Are you understanding that mathematics? If you're not understanding, you can revise the approach. Should we proceed? Yeah? So open the brackets, upper brackets. We're going to be having 300. We have 20R plus 300 plus 15R over 20 plus R will give us the total resistance R. Hey, by the way, total resistance, we call it different from this R. So that this is now going to be having 35R plus 300 divided by 20 plus R. That is the total resistance of the circuit. Are you getting it? Now you are going to say, from Ohm's law, V is equal to I, R. The total voltage for the circuit is what? 5. Total current for the circuit is what? 0.2 times R. Now the R we are talking about is this. So it is going to be 35R plus 300 divided by 20 plus R. So now I'm going to solve for R. Are you following on this step? This Ohm's law, the only thing we wanted is to find R. Actually, it is R prime. So you can now open the bracket once again. Help me with the manipulation. 0.2 can be 35. Oh, don't do that. Just divide both sides by 0.2. 5 divided by 0.2. Yeah. So this 25. So this is 25 equal to this 35R plus 300 over 20 plus R. So you can cross multiply. 20 times 25 we get 5,500. 500. Then plus 25R is equal to 35 R plus 300, isn't it? Now we collect like that. So I take the 25 this side and the 300 the other side. 500 minus 300 is equal to 35 minus 25, isn't it? So this is now going to be 10. 500 minus 300, what do you get? 200. Therefore, R is equal to what? 20. 28. Which of the two outputs is easier? The first, the second. The first, the second. The second one has what? Too much math. What is that too much mathematics? The issue is just fractions. The major problem was finding expression for the total resistance. Then the only formula you're substituting in is this one. That's all. Okay. I wonder whether we can proceed to the next number. So, no. There was also to find power. Power dissipated in R. That one is going to be very easy, isn't it? Power is equal to I squared R. The current was 0.1 squared. And the resistance is 20. So the final answer is what? 0.2. Hope that is the answer you got. Watts. 0.2 watts. Watts. I don't know which approach has become convenient to you. Or you are sticking to the first one. No, any of the two you like, you are. Okay, we have off. All right, we go to question 2. Figure 2 shows a battery of 24 volts and negligible internal resistance. The figure was like this, but we had the two resistances. So this was 8 ohms, 6 ohms, 3 ohms, 8 ohms. So the question was, find the effective resistance of the circuit. Find the effective resistance of the circuit. Now this question is funny in the sense that once you fail Roman 1, the rest will not help you, because the answer for the first one will lead you to the second one and the third one. The second thing is that I'd provided answers hoping that you try as much as possible to get those very answers. But the fact that I didn't get feedback it implies that either we are negligent to do, or the next questions were extremely tough on our side. But I'm happy to note there is one person who sent me an answer. It was called Watsema Timber Sugar. I was so impressed, and the answers were correct. So how I wish that all of you embrace the same idea of participating and sending answers. Effective resistance of the circuit. Now, we only need to identify which resistors are in parallel, which resistors are in series. Now let me use my friends that are closer here to tell me which of the two resistors are in series and which are in parallel. Yes.
8 and 6 are in parallel. Then 8 and 6 and 3 are in series.
Yes, that is her thinking. What about you? Which of the two resistors are in series, which resistors are in parallel?
The ones in series are 6 and 3. Parallel are 8 and 6.
Hoping that you have noticed that it is 6 and 3 that are in parallel. 8 is not in parallel, 8 is in series. Because the cell here supplies current. When current reaches here, that's when it subdivides. And in series, current must be the same. But where you see subdivision of current, it implies we are now in parallel setting. Are you getting it? And you could say the terminal here and the terminal here are being joined by the two resistors. Are you getting it? So it implies the two resistors are in what? Parallel. The resultant of which is going to be in series with the 8. Are you noting that? So, in parallel setting, so effective resistance, I'm using a summary, resistance R is going to be product of a sum. 6. 6 by 3, and then 6 plus 3, plus 8. 6 by 3 is 18, 6 plus 3 is 9, 18 over 9 is 2, 2 plus 8 is 10. 2 plus 8 is 10. I hope that first part of the question was extremely very easy. And the answer was indicated 10. So that is Roman 1. So Roman 2. Current flowing through the 3. The rest of the questions are now very easy. Current flowing through the 3. Now you can't find current flowing through the 3 before you get the total current in the whole circuit. So let's get the total current in the circuit. Total current I is equal to V over R, where V is the total voltage in the circuit, which is 24, divided by the total current, which is 10. So that one you are going to get the current to be 2.4 amperes. That is the total current in the circuit. So now, to get the current through the 3, there are two approaches. Either, why should we use two approaches? We only one is enough. Let's get the PD across the parallel setting. So PD across the parallel setting. We call it V parallel. is equal to the total current in the circuit times the different resistance in the parallel setting. So this is now going to be, the total current is 2.4. The resistance in the parallel setting is actually 2. When you're noting that, parallel setting is that. So the PD now is going to be 4.8 volts. That is the PD here. Remember, we say the EMF here of 24. There is a supply PD here, and the PD across the parallel. When you add V2 plus V1, you get total of 24. Are you getting it? So that's why, if you want to current through the 3, you first need to get the PD across the parallel of which the 3 is part. So now, you can now find current through the 3. Current through the 3 ohm resistor is going to be equal to, let me call it I1. Let me call it I1, I2, subdivided. So that is going to be equal to V for the parallel setting times resistance of the 3. So that is going to be equal to 4.8 divided by 3. And 4.8 divided by 3, what do you get? 1.6 amperes. Isn't that the answer we get? Yeah? That is the answer. Yes, it was 1.6. Lastly, we are to find the power dissipated in the 3 ohm. Power dissipated. Power dissipated is I squared R. The current I through R is already 6, 1.6, and R is 3. And therefore the power dissipated is going to be 1.6 squared times 3. What answer do we get?
Yes, 7.6.
7.6 meters. Have you seen serious challenges in the activity?
So current through the 3 resistors.
Pardon?
The current through 3 ohms. The resistance.
That's what the question is asking. The question is asking. Find effective resistance of the circuit current in the 3 ohm resistor. That's what we are doing.
The other one, the dot one.
Which one?
The only one for the 3 ohms.
3 ohm?
Yeah.
That's the only one they want.
So what about if they want it for
The 6?
And the 6?
If they wanted the 6, there are 2 approaches. We could get the total current, which was 2.4 minus 1.6. Yeah? Or you could still say that I2 is equal to V parallel over R2. V parallel is 4.8 over 6, which gives
0.8.
what?
0.8.
0.8. Like that. Now you got add 0.8 plus 1.6. But you get 2.4. Yes, that's what I'm saying. So you can use many forms. Either you just get this one, subtract from the supply current of 2.4, or use the same formula you used to calculate the 3 ohm resistor current. Is that one okay? So if you permit me, we can continue. Should we proceed? We go to activity 2. I wonder which answers you did. But question 1. But you need to note, these physics calculations need practice. The more numbers you practice, the more conversant you will become for all the new tricks that are coming. If you only stop on the numbers that I've given you, then you will not achieve perfection. You get me? So we continue. Activity 2 is about cost calculation. We told you calculate the cost of running, number 1, electric fire alarm for 2.5 hours if it takes 13 amperes on a 100-volt supply, and each unit costs 400 shillings. We said to calculate electrical cost is equal to what? Electrical cost is equal to what? PTC. Isn't it? Electrical cost, we simply say it's equal to what? PTC. Now we are looking. Do we have the power according to the question? Eh? No. Can we get the power according to the question? The answer is yes. How do we actualize it? Power is equal to IV. But power is equal to IV. The current was given to be 13 and the voltage 100. So therefore the power is 1300 watts. Were you given the time? That means the answer is too easy. Therefore, electrical cost power 1300, but you want to say power in kilowatts. Remember, power in what? In kilowatts times time in hours. We are given 2.5 hours. 2.5 hours, how do you write it? 2.5 hours times the cost per unit. Can you evaluate and see what you are getting? I can see. So it is 130 times 2.5 times 4 is already 10. 10 times that 130 is 13. I only add another 0. Isn't it? And was it in shillings?
Yes.
In shillings is the same amount. Isn't that the answer we gave?
Yes.
What did you get? Are you realizing that the question was as cheap as that? So that was question 1. Question 2. A 2 kilowatt electric fire alarm is used for 10 hours each week. A 100 watts bulb is used for 10 hours each day. Find the cost for each week if a unit of electricity costs 300. Now you need to be careful. How I wish you do them separately. Otherwise, we're adding things of different timing. So you need to separate them. So let's begin with fire alarm. power for the fire alarm. Yeah? Power is going to be what? 2 kilowatts. It is being used for 10 hours each week. And they want, but that means for a whole week, total power for the week, yeah, is going to be 2. Let's get the cost right away. Cost for the fire alarm is going to be PTC. Power is 2 what? Kilowatts. Time is how much?
10 hours.
How much?
10 hours.
10 hours a week. Times cost per unit?
300.
300. This one gives 6,000 shillings. Only for the fire alarm, we are spending that amount. Yeah? Per week. Now let's see. When we deal with the which other one? For the bulb. For bulb, cost is PTC. Is going to be equal to
100 divided by
the power is what?
100.
100 watts. How many bulbs do we have?
One.
Only one bulb. So that's 100 divided by 1000. Times
10
time is what?
hours.
Each day. So they are saying 10 hours each day. So 10, therefore for a week, 7. Are you noting it? Because we want for a week. Each day is 10 hours. That means for a week multiplied by 7. Then times 300. So we can now simplify. So we get 7 times 3 is 21 times 1,000. 100. 2100. Now, total cost. One total cost. So total cost for a week. Is going to be 6,000 plus 2,100. So we get what? 8,100 shillings. The answer is different. Yeah, that is the real answer we're giving. That is for people who don't want to disturb themselves with a lot of mathematics. You do one separate and do another one separate. Are you getting it? Are you getting it? Or what you can do, alternatively, if that is not convenient to you, you can simply say power cost is equal to number of kilowatt hours. Number of kilowatt hours, these are number of minutes. Yeah? Times what? Time. Times unit cost. Yeah? Times what? So what you can do, you can now say for the fire alarm, the kilowatt hour, we had 2 kilowatts times the number of hours. Plus, now we go for the bulb. The bulb, we had 100 watts, convert to kilowatts, times the number of hours, 10 hours times 7. Now, the whole of this one, Those are number of kilowatts. Yeah? You multiply them by unit cost times the unit cost of 300. I don't know whether I understand what I'm doing. In fact, if you don't want, I'm using another shorter means for people who don't want to spend a lot of time. Are you getting me? Instead, the cost is equal to number of kilowatts. Because number of kilowatts is the same as PT. Are you getting me? It's number of kilowatts. Are you getting me? So someone, what he does, gets number of kilowatts for the bulb, for the fire alarm, plus number of kilowatts for, and multiplies all of them times time, times the cost for each unit. Then here, you simply do like this. It's simply 20. Now you could see here that we have remaining without the 7. So this is going to be 20 plus 7, so it is 27. 27 is the number of kilowatts, kilowatt hours. When I say number of kilowatt hours, I mean number of units times 300. So answer will be 27 times 300. Yes. Now someone who has done like this 1, 2, 3 steps will earn the same marks as someone who has done that together. Don't say, is it fair? Yeah? Yeah? It is very fair. For a reason is that this one is more intelligent than this one. Yes, because it's able to summarize the whole concept in a shorter period of time. Okay, so that is number 2. We got number 3. You realize that calculations of electrical energy and costs, they are very easy. We got to number 3. But if you don't trust yourself in this short method, don't try it. You stick to splitting and then adding. Split add. Or you can just do like the way I've done it. Then we go to the next part. A house contains 3 60-watt lamps, 2 100 lamps. They are switched on for 8 hours. If a unit costs that, how much money should be paid? I think this one was too easy. Yeah? All of them are in the same dimension. So you can now get total power for 8 hours. Oh, this one is straightforward. Electrical power is PT. So total power is going to be what? 60. Yeah? But remember the other are 3 lamps and these are 2. So what do? We get total power. Power is going to be what? 60 times what?
3
Plus
100 times 2.
100 times 2. And then we get the total power to be what? 180 plus 200.
208.
I thought 380.
108
Eight.
308.
380. So this is going to be 380 watts. So you can now go to our formula. Electrical cost. The power, the time is the same. 380 times, what was the time?
8.
Huh?
8 hours.
8 hours, and the cost per unit?
250.
250. And the answer is? The answer is what?
760.
It is
760.
700. Now I get a different answer. What answer?
760,000.
760,000. I even failed the answer. I had written 4,000. Okay. So the answer is?
Teacher, wait.
Hmm?
We have to divide the words by 1,000.
Oh, but still, even if we do. So multiply 380 times 8 times 240.
760.
Which is 760. Like that. Okay. I've agreed. So people must have suffered on that one. Hmm? Then number 4. Number 4. A 2 kilowatt heater used for 10 hours and 100 lamp is used for 8 hours each day. Find what? The total cost paid for electricity at the end of the month of September. And each unit costs 500. Now, what should we do? We separate or we do the shortcut method? Shortcut method. Someone is suggesting that we use a shortcut method. So we're now going to say electrical cost is equal to number of kilowatt hours times unit cost. So the number of kilowatt hours, we have one for the heater, which is 2 times 10. Hmm? 2 times 10, but remember 10 hours for what? For every day. 10 hours and are used for it each day. So that means you multiply by what? By what? By 30. September has how many days? 30. Hey, another day they will tell you another month of March and you multiply by 30. So September is 30 multiplied by 30 plus 100 out of 1,000. It was only one lamp. Times 8 times 30. Then all of them times, what is the unit cost? 500. So we simplify. This one can go with this. So remain with 2 times 3 is 6. So that means, this is 600.
Yes.
600 plus 8 times 3, 24. All times 500. So 624 times 500, what do you get? 312 shillings. Was this the same answer given? Yes, I think it is the same answer.
Yes.
The same answer. So that was one approach. You're going to say, now we are giving two formulas. You have PTC and then you are giving now the other one. It is the same formula. Are you getting it? Because number of kilowatt hour is the same as P times T. Number of kilowatt hours. Same as P times C. The reason why I say the number of kilowatts is because I wanted you to add power times time plus power times time. Alright, we got number 5. And this, I think this was a calamity number because it involved some concepts you have not covered under heat. It was saying electrical heater is immersed in 0.05 kilograms of oil in a calorimeter with negligible heat capacity. The temperature rose from 20 to 50 in 100 seconds. If the specific capacity of oil is 2000 joules per kilogram per Kelvin, calculate the power supplied by the heater. Usually, power supplied by the heater is equal to power supplied by the heater is equal to what? According to what we are given. The power is going to be equal to what? We are not going to tell you now. Power, we know the formula, there are 3. There is P is equal to IV. We also have P is equal to V squared over R. Another one is what? I squared R. Now, of the formula, none of those is working here. But you need to know that power is the rate of doing work. And work here is converting electrical energy to heat energy. So power is work over time. And the work this time around is heat energy over time. Are you getting it? So now we'll be converting the heat energy divided by time. Now the heat energy, according to the question, is given in terms of heat supply. So we are now going to say heat supplied is equal to mass times capacity times temperature change. Now, according to the question that we have, the mass was given as 0.05. Specific heat capacity for oil was given as 2000. And the temperature changes are changing from 30 to 50. So it's going to be 500 minus 50 minus that was it 30 to 50? 20 minus 20. So in this case, we are going to get the heat supplied, which I'm using H. It's going to be, can you evaluate with your calculator? Or we are used to evaluate like the way I do. Okay, no problem. This is 30. 3 times 2 is what? 6. Yeah? Meaning that this is going to be 60,000. 5 times 6 is what? The total answer is 3,000. 3,000 joules. That is the heat. So you can now get the power supply. Power is now going to be equal to what? Power, electrical power P is now going to be equal to H over T, that is 3000. And what was the time? 100 seconds. So we get the answer to be 30. Was the answer given 30? Yes. The answer is 30 watts. It is 30 watts. That was for part 1. That is Roman 1. Was the question too complicated? The only aspect that was lacking is only this formula. Heat supply is equal to mass, specific capacity, times temperature change. Change is differences in temperature. So we get that, then we can now get the power. Roman 2, power supplied by the heater is done. Cost of running the heater for 100 seconds each day for 48 days. What are we going to do? Power. Cost, electrical cost. Is going to be equal to PTC. The power is 30 watts. We convert to kilowatts. Isn't it? And each day, what are we consuming? The time is? The time is 100 seconds. We need to convert the seconds to hours. How do you convert seconds to hours? Time is 100 seconds. Each second has how many minutes? 60. And each minute has how many? So I think we have converted now the seconds to hours. Sure. Yes, you have done. Then, cost per each unit. Hey, how many hours? For 48 days. This is 1 day, this is 48 now. Times the cost is 400. What is the final answer? Okay, finally all simplified. This one goes with this one. And this one goes with that. So I'm going to remain with 3 times 48 times 4 divided by 36. 3 times 48 times 4 divided by 36.
16.
16 shillings only. I think that was the answer that was given. Okay. So, lastly, any assumptions made in this calculation? Yeah. The first assumption is that the heat supplied by the heater there was nothing lost. All the heat supplied by the heater led to a temperature rise of oil. Are you getting it? But practically, it's not possible. Even if you are cooking using gas, some heat is lost. When you are there, you feel some heat, meaning that not all the heat that we are supplying is getting used to cooking. Are you getting it? So the assumption is what assumed to be true is that the heat supplied by the heater was heat gained by the oil in the calorimeter. Are you getting it? So assumption no heat heat was lost or gained from the environment or from the surrounding. That is what you assumed, such that the only heat you are using is that one. You assume that there was no heat lost or gained from the what? From the surrounding. It is the same explanation by assuming that all the heat we supplied was all used, and none was lost or gained from the environment. Are you getting it? Now time is not enough on our side. So our interest today, all along we have been going through the previous one, is application of electrical heating. So far, we studied electrical energy and power. And we have realized whenever there is electrical energy, power, there is some heat. Electrical energy is converted into heat. So therefore, we need to know where is that heat used. How important is the heat obtained from electrical energy? Now you do well to remember, we said, sometime when we are talking about resistance, we said when current is passing through a thin wire, when current passes through what? A thin wire. The wire heats up, or there is rise in temperature. And we explained the cause of temperature rise. We said when the conductor or wire is connected to the supply voltage, electrons are accelerated by the electric field from the battery. Accelerated means you increase the speed of electrons, speed at which they are moving. These electrons gain kinetic energy. When you increase speed, you gain what? Kinetic energy. Now the gain in kinetic energy, the heat they get, they collide with atoms of the conductor. They collide with atoms of the conductor. Assuming, let me illustrate what I'm talking about. I'm saying when a conductor is connected, say a wire, thin wire, connected to supply voltage, the electrons are accelerated. The electrons, usually the electrons move like this. These electrons tend to find metal atoms within the conductor. So these electrons gain kinetic energy, and then they collide with metal atoms. So when they collide with metal atoms, they lose some of their kinetic energy to the metal atoms. The metal atoms themselves also are made to or vibrate, colliding with each other, creating that friction that causes the heating effect. So that is the reason why any wire carrying current creates a heating effect. Now, what we are saying, how important is the heating effect in electrical appliances? So we are saying electrical appliances that use heating effect are: 1, electric bulbs and tubes. These bulbs we are using to give us light, they first convert it to heat. Even this energy saver is so-called energy. You even experience some heat from them. 2, electric flat iron. The flat iron, it is also providing, in its mode operation, there is some heat. Electric kettles, and also cookers. Are you getting it? But you are not mentioning refrigerator. Much as we know that there is some heat that is expelled at the back of the refrigerator, but that heat is not of any use to us. So when we talk about applications, we talk about practical uses that are beneficial to us. So now we are going to be talking about one at a time. We begin with, you can look at the diagram of the filament lamp. When I talk about filament lamp, I mean the bulb, the normal ordinary bulb. Now look at the diagram. You could see inside the tube, there is a filament. You see the filament? There is a filament. There is also wires connected to the filament. Then there is also argon or neon gas, sometimes nitrogen. So it is an inert gas that is placed inside there. And there is a bayonet cap, and then the connection that you connect to the holder. Now, how does it work? We said that it consists of a filament made of tungsten. Tungsten is a metal, a highly conducting metal, which dissipates so much heat that it becomes quite hot. When it releases heat, it becomes what? Hot. And it emits light. It emits what? Emit means gives out what? Gives out what? Light. We are saying that it is filled with an inert gas like neon or nitrogen or argon at reduced pressure. What do you think is the role of neon or an inert gas at reduced pressure? The purpose is to prevent evaporation of tungsten, because when it heats up, we expect it to evaporate because too much heat. So to prevent evaporation of tungsten, and also increases on its operating temperature, because you see, much as tungsten is a metal of high melting point, but the too much heat that's generated may make it what? Melt and evaporate. So it is that gas. Inert means unreactive. So it prevents the quick reaction of tungsten on heat, so that it maintains within the operating temperature. Otherwise, it condenses and blackens it, because if it is going to heat up, it will condense on the tube, and the tube will become black, therefore the light will not be seen. So we're saying the efficiency of the bulb may be improved by using coiled filament, which reduces the space. Coiled, not coiled. Coiled. You can make adjustment to that. The word is coiled, not coiled. 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 You see, you increase the surface area. You use a longer thing with a smaller. When it's coiled, it uses smaller space. So it reduces the rate of heat by convection. Limitations of the filament lamp. Why are people now these days losing interest in these bulbs? The filament lamps, I mean the ordinary bulbs. Why are people losing interest? It is because of the following limitations. One, they are inefficient, since most of the electrical energy is converted into heat energy. They're usually hot. Have you ever happened to touch it? That's why even when you are replacing it, you just use a piece of cloth, and then you remove. Why do you use a piece of cloth? It's hot. Are you getting it? So it is releasing a lot of what? Heat. So there is a lot of heat conversion of electrical energy being converted into heat. Yet, in lighting, we don't want heat. We want them to provide light. But instead, it is doing what? Providing a lot of heat, which is unnecessary. And that one brings up another second reason: they are uneconomical to use. Because most of the energy is converted into heat, and therefore for us we pay for power. We pay for power. And the power we are paying is just wasted into heat. Therefore, it is uneconomical. It is consuming a lot of electrical energy. And lastly, they do not last for long. They do not last for long. This heat dissipation wears them out so fast. So you end up buying periodically. Those are the inefficiencies. And this one brings about, in order to improve on the filament lamps, that's why we come up with fluorescent tubes. Fluorescent what? When I say fluorescent tube, do you understand what we're talking about? We are talking about these tubes. Not these other tubes. Now, look at the diagram for the fluorescent tube. You are noting we are having two electrodes, that is the cathode and the anode. The cathode is where we are producing the electrons, and the anode is where the electrons are accelerated. Then inside, we have mercury vapor, we'll see its use, then glass tube, and also we have what we call fluorescent powder. We are going to see the use of all those things that are placed inside there. Now we are saying, how does it work? We are saying when the tube is switched on, the mercury vapor emits ultraviolet radiations. The mercury vapor emits ultraviolet what? Radiations. These radiations strike the powder. The other, we said the fluorescent powder. Fluorescent powder usually could be zinc sulfide or those elements that easily glow. So it emits ultraviolet radiation that strike the powder. So the powder glows. I'm not saying glow. You see, there are some people who cannot distinguish between R and L. Glows. Here in the central, R they call it L. And in the west, L they call it R. So here you need to be careful with the word you are using. We're using the word glow. Glow means you are giving out light, but you're not giving out fire. Are you getting it? You are giving out light, but glowing. Like, yeah. Not to explain it better than that. Okay, so the color of light emitted depends on the color of the powder. So if you want the fluorescent tube to emit white, be sure that it is a white powder. If you want it to emit green, you use green powder like that, and then you produce the required color of your interest. That's in brief how fluorescent tube works. Is there any question as far as the fluorescent tube works is concerned? Okay. 4. There is a
On how the fluorescent tube it only ends on when the tube is switched on. The mercury vapor emits.
Yes, what?
So it ends there.
Can you have a look? Hey, okay, we'll update some little missing. Alright. We are saying when the tube is switched on, the mercury vapor emits ultraviolet radiations. The radiations strike the powder and the powder glows emitting light. And say the color of light emitted depends on the color of the emitted what? Powder.
But
But there is something also missing. There is something to do with the was to do with energy savers. Saving light. We'll update it in the next notes for the next lesson. Okay. Now the last one is the electric flat iron and kettle. For them there is a heating appliance containing a heat element, often made of nichrome wire. That element, heating element, is made of nichrome wire. Nichrome is an alloy of nickel and chromium. The nichrome wire is used because it does not oxidize when it becomes very hot. So essentially, current passes through the nichrome wire. The nichrome wire heats up, and therefore the water you have placed inside could also get the heat from the nichrome wire. Our time has almost gone, but let me briefly talk about domestic electricity supply. Under this topic, we are going to learn the following. Describe advantages and disadvantages of series and parallel connections. Correctly identify 3 pins and wire them. Mention practice safety precautions when wiring a house. Explain the necessity of earthing some electrical appliances. Demonstrate proper positioning and uses of switches. And then state advantages and disadvantages of different lamps. Already the different lamps, we have talked about them, but we will be talking about the detail of what? Electrical wiring. I don't know how many minutes I'm left with. How many? 13 more minutes. Okay. So we are going in these minutes. We are going to talk about safety devices and then electrical wiring. That's series and parallel. The details of domestic wiring will be covering in the next lesson, if at all it is there. So safety devices. 1. Fuse. A fuse is a short length of a thin wire of low melting point, which breaks when the current exceeds the safe value. In other words, if current is too much, the fuse melts and disconnects the circuit. So it is saying it is a protective resistor that melts when there is excessive current flow. If the other words are too many, you can simply say it is a protective resistor which melts when there is excessive flow of current. And I'm saying it melts and breaks the circuit in case of overloading. Overloading means you have allowed too much current to enter. Or short circuit. We are going to see short circuit, the meaning of short circuit, briefly later. So switch in the live wire, switch off the live wire, which breaks and then completes the circuit. Then we have another one called circuit breaker. The circuit breaker is used to disconnect the mains current when there is excessive accidental earthing of the live wire. Usually, but these days circuit breakers are modified into checking on tenants who want to use excessive current. Are you getting it? So they are connected with circuit breakers so that any excessive thing, the thing disconnects. Then you need to come to the landlord and say, my power is off. And then say how you're using it beyond your capacity. So 3, earth wire. Earth wire, this one conducts a well leaking charge, preventing electric shock. all the appliances like fat iron and the rest are connected with what? The earthing. So how the earth connection prevents electric shock? How does it do it? So you're saying the earth wire connects the metal case of an appliance. When I talk about appliance, I mean flat iron, refrigerator, cooker, and so on. All those are electrical appliances, including heaters. So we connect the earth wire to the appliance and then to the ground. The base. We connect it to the base that will be touching the ground. Now, if the insulation of the live wire wears out, insulation, no mean insulation, the wire that is covered in the live wire. You understand when I say live wire? Not in your meaning. I mean any wire like the other one. This carry. Then out then like that one. So any live wire that is carrying current, the insulation may wear out, such that the live wire comes into contact with the neutral wire. So there we expect, when they come into contact, we may expect some electric shock. So what happens? The earth wire carries away the current to the earth. So the fuse in the live wire will blow and then cuts off the supply. So in that way, the earthing prevents electrical shock. Then electric wiring. Electric wiring here, before we go to the actual wiring, there are some key things we need to note. We are saying there are two ways in which electric connections can be performed. We could connect the connections in series or in what? Parallel. So when you connect in series, we are just connecting the current, the mains current. You can connect one bulb here, another one is the heater, you can call it resistor, and another bulb there. This is bulb 1, we call it lamp 1, lamp 2, and this is a resistor. So you realize that when current is coming, there is a PD that is developed here, V1, V2, and V3. So this one tells you that inside this connection, each lamp has a different PD depending on its resistance. Then how is the advantage and disadvantage of that? We are saying, first of all, the current is the same because they are in series. The current is what? The same. Disadvantages of series connection. Why don't we connect most of the lamps in series? These are the reasons. One is that if one appliance is faulty, like this one, if it's, for example, its fuse blows, the rest will not work. Are you getting it? The reason is that current has to flow through one to go to another. So when there is a roadblock here, then you cannot proceed. Are you getting it? So that's why we are saying that a fault, or when one appliance is switched on, all other appliances will go off. That is one disadvantage. The second disadvantage is that it requires a very large voltage to supply them. Because there's going to be PD loss, potential loss, there are going to be many losses in PD because they are in series. So that means you need to have a very big power supply for all the appliances that you need. Are you noting that? So that is the reason why we don't connect wiring in the house in series. Are you getting it? But we are not saying it is not possible. There are circumstances where you may need it. For example, there could be a dormitory, and you don't want to make many switches. Are you getting it? You connect them in series such that you only use, for example, if you're a matron somewhere and the students are not switching on their lights, you order the electrician to make a series connection such that you only switch off in your bedroom. Time off. All of them are off. Are you getting it? That one is only possible in series what? Connection. But in parallel connections may not be possible, as you are going to see. Now, parallel connection. Parallel connection. Usually in a house, umeme supply is a voltage of around 240 volts. Now, if this is the supply voltage. That is the supply voltage. If you want to connect in parallel, you have to have two main lines. One line is carrying live wire. Live what? Live wire. And another line that you are connecting in parallel with the first one is carrying neutral wire. Neutral. But now, these are the bulbs. You can have bulb 1, bulb 2, and bulb 3. You want to connect them in what? In parallel. So here, you get the fuse. Because the fuse is usually connected to the live wire. That is the fuse. It goes, does not mix. You see, I'm doing this thing I'm doing. It implies that when I carve it like this, it is passing on top. This is switch K1. And then here, we connect to the live wire, the neutral wire. The circuit is now complete. Then we go to the second one. There's a fuse here. Fuse 1. Then fuse 2. Here you can have K2 and then connect to the neutral wire to complete the circuit. Same applies to the third one. K3. Then you connect to the live wire. This is fuse 1, fuse 2, fuse 3. These are lamps. Lamp 1, lamp 2, lamp 3. And this is the supply voltage from the socket, from the wiring in. Now, you want to connect the bulbs in parallel. You get one wire comes from the live wire. Up to this is your switch. And another wire, because for you to complete the circuit, it has to, the beginning, the one that's letting in is live wire, and then taking back is the neutral wire to complete the circuit. So one is connected to the live wire, this is neutral wire back. So when you close the switch here, this one lights. But this one does not necessarily light. Are you getting it? And when you can decide to, even if you decide to close switch K2, lamp 1 and lamp 2 can light. Are you getting it? So in other words, when you connect bulbs, or when you are wiring a house, and then you connect them in parallel, you have freedom. There's more freedom. First of all, the PD is the same. PD is the same. The second thing is that each room has each independent switch. A fault in one room, or one bulb blows, does not affect the rest of the other bulbs. So these are the advantages of parallel connection. One, if one appliance is fault or switched off, the other appliance is the circuit remain unaffected. Two, different current flow through each of the components in the parallel connection. Three, all appliances will be on the same PD and therefore work normally. Three, there is no overloading, meaning that there is no too much current that can flow through a bulb because there is a fuse that regulates the amount of current that has to pass through. And then you are saying a short circuit in one appliance does not affect the other appliances. Then we are ending with these two notes. One, in electrical wiring, each appliance is connected in parallel, has its own switch and fuse, like the way we are seeing there. Each has its own fuse and switch. Two, short circuit. What do you mean by short circuit? We are saying a short circuit is a path of low resistance. Is a path of what? Low resistance. Short circuits usually occur when the live wire gets directly in contact with what? The neutral wire. When the live wire comes in contact with the neutral wire, especially when the insulation wears off, what it causes a large amount of what? Current to flow between the two wires. And since both have low resistance, therefore current results from the short causes overheating of the wires. So they spark and they sometimes cause some fires of no. So we need to ensure that there is proper insulation of the live wire so that it is not in contact with what? With the neutral wire. So there will be a small activity which you will do. It has only 3 numbers. And all of these activities are rotating about parallel and series connection. Are you getting it? So it is 1, explain why the fuse is always fitted to the live wire in an electrical appliance. The power rating of an electric bulb is given 24 watts, 240 volts. Calculate the current through the filament and resistance of the filament. You're going to say, no, we have not had that one. Yes, you know the role of a fuse, and therefore it can be used to regulate. You have been given the power and the voltage. You know the amount of current and then relate it to the fuse use. Then the third one, if given the fuses of 3 ampere, 5 ampere, and 10 ampere, which fuse is most suitable to be used in the other power rating? You analyze the question and see. Then number 2, you have arrangement of bulbs. One bulb, the bulb B1 and B2 are connected in parallel. And then B3 is connected in series. So the questions are, which bulb will light brightest when K1 is closed? I don't want someone to say bulb B. Give a reason. Are you getting it? You say bulb B1 because ABCD. Then, if bulb B1 blows, you see where B1 is. If bulb B1 blows, what will happen to the other bulbs? Lastly, if bulb B2 blows, what happened to the other bulbs? Then, lastly, no, this was supposed to be B3. If bulb B3, you make that correction, I did not notice it. No. If bulb B3 blows, B3, I wrote B2, but supposed to be B3. If bulb B3 blows, what happens to the other bulbs? Then lastly, number 3, state the use of the following wire in the building: a fuse, a switch, then the earth connection. B, explain why the space in the filament lamp is filled with an inert gas. C, you are provided with the following cells, switches, 2 bulbs, connecting wires. By means of a circuit diagram, show how the circuit can be arranged in order to have maximum brightness. And lastly, explain how earth connection prevents electric shock. Thank you so much for today. It has been a lengthy lesson, and I applaud you for that patience in learning and sharing knowledge with us. How I wish you